Okay, the big thing in this section is what we get if we start trying to diagonalize a symmetric matrix. So if A is symmetric, then when we diagonalize it into PD P inverse, then we can do it even more. Like we can go one step further. We're just having P as an invertible matrix. We can actually make it so that P is the matrix that we use for P is actually an orthogonal matrix. So these are orthogonal matrices. And then, so we don't have to go to inverse, we can simplify that to transpose. So D is the same. It's a diagonal matrix with the eigenvalues down the diagonal. Doesn't matter what order we put the eigenvalues. We just have to put the columns of Q in the corresponding order, and the rows of Q transpose in the corresponding order. So that's the big thing. This is called the spectral theorem. And the spectral theorem says if A is a real n by n matrix and A is symmetric, then A is symmetric if and only if A is orthogonally diagonalizable. Okay, so A is a real n by n matrix means the values are real. They're not, there's no imaginary parts in any of the entries. So if A is symmetric, if and only if A is orthogonally diagonalizable. So if you know one, you know the other one. So if you know it's symmetric, you know it's orthogonally diagonalizable. If you know it's orthogonally diagonalizable, it has to be symmetric. One of the problems, there's a few things that you have to show, like a few proofs in your homework. And you have to show things like if A and B are orthogonally diagonalizable, show that A plus B. Well, the easiest way to do that is just to show that they're symmetric. If A and B are orthogonally diagonalizable, A and B are symmetric. So NA plus B is symmetric if both A and B are symmetric. So then by the spectral theorem, A plus B has to be orthogonally diagonalizable. So it's pretty straightforward once you, if you can show that they're symmetric. A few, let's see. Just a reminder, the eigenvalues of in a symmetric matrix, as long as the eigenvalues are distinct, the eigenvectors are orthogonal to each other. If you have multiple eigenvectors from a single eigenvalue, so it has a multiplicity of 2 or larger, then you're not guaranteed that those two are orthogonal. You might have to do Gram-Schmidt to orthogonalize one of those, or however many. And is that all the important definitions and theorems? Oh, let's talk about, so this is the spectral theorem. There's also something called the spectral decomposition. And the spectral decomposition, it takes this structure, and when you start multiplying it out and do a little algebra, you get that you can write the matrix A as Q1 times lambda 1 times Q1 transpose plus lambda 2 Q2 Q2 transpose plus dot, dot, dot down to lambda n Qn transpose. So someone in the other class wanted to show an example of how do you actually write that down. So let me pull this up and we'll do a quick example. This is just from the first example of this section. So all you have to do is know the eigenvalues and know your Q. So in example 5.16, it gives A as 1, 2, 2, and a minus 2. And it's symmetric, so it's orthogonally diagonalizable with D as a minus 3 and 2 on the diagonal. And Q is 1 over the square root of 5, a minus 2 over the square root of 5, 2 over the square root of 5, 1 over the square root of 5. Okay, so so I have A, I have D, I have Q, but if we want to write it out like this, then I'm going to take Q1 and Q2 and just start plugging in the formula. So A, this is equal to, sorry, that matrix A has taken on a shear transformation. So I apologize for that. My screen is still up. It's not down like on the table when I usually do it when I'm making videos. So it's a little harder for me to write on it. So a -3, and then Q1, that's going to be my first column of Q. So 1 divided by the square root of 5, a -2 square root of 5. And then that transpose is 1 square root of 5, a -2 square root of 5. And then add that to lambda 2, which is 2. And then Q2, so this is Q2, this is Q2. So 2 over the square root of 5, 1 over the square root of 5. And the transpose, okay, so A we can rewrite as this, and this is the spectral decomposition of A. Okay, we could multiply that out so that we get A is equal to a -3. I can take the -5 times the 1 over the square root of 5 times 1 over the square root of 5, which is 1/5. And then a -2/5, a -2 times the square root of 5 over the square root of 5 times 1 over the square root of 5, which is a -2/5 again, and then 4/5 plus 2. Let me just do that. These are called outer products instead of inner products. This outer product form. This will come up again in the singular value decomposition. So okay. So so this is just the spectral decomposition of A, where we've multiplied out those outer products to get 2 matrices. All right, so that's a quick summary of this section. What questions do you guys have?
Would those last two just be over 5 instead of over √5?
Oh, yes. Thanks. I mean, I knew that. I was just making sure you were paying attention. So. Okay, other questions?
If this was a problem on the test, we could just leave A in that form, correct? Just like the eigenvalue and the Qi and Qi transposed product.
I would probably go to I'd probably go to this one. In the keys that are written up from past finals, that's what they have. So I would.
But we don't have to simplify it further.
No.
Perfect.
I would multiply it out. So. Okay.
If we simplify it further, it would just bring us back to A, right?
Well, right. Well, yeah, if you multiplied the -3 in and the 2 in and then actually added.
Oh, yeah.
Yeah, it would. But yeah, this is how I've seen it written quite a bit, is just to keep the eigenvalues out, and then you have these rank 1 matrices. So, okay, other questions? Boy, the last class had lots of questions. Well, I have questions for you if you guys don't have questions. So, let me share another screen. So this is from one of the practice finals or previous finals. Oops. Not sure if that's big enough. Can you guys see that? Problem 6, okay? Okay. All right. So think about this one for a second and try to figure out which one of these is true, which means it's always true. This is where I should put you in breakout rooms, but you can't see my screen if I put you into breakout rooms. So I would have had to post this in a different way. Thanks. Take another minute. All right. How about A? Is A transpose? Okay, so we know that A is an n by n matrix. It's orthogonally diagonalizable. Which of the following must be true? A transpose A equals the identity. What do we think about that one? You guys can do your, if you want, you could do thumbs up or thumbs down or yes and no on these. So. Okay, 3 people have responded, 4 people have responded. Okay, 5 or 6 people have responded. Okay. So I see about we're about half and half. So, okay, so A transpose A, does that have to be true? It doesn't have to be true. That means A transpose is the same as A inverse. If you could multiply the transpose times A and get the identity, it means that it's the inverse. That means that A is actually an orthogonal matrix itself. But A doesn't have to be an orthogonal matrix to be orthogonally diagonalizable. It just has to be symmetric. So although there might be some A's where that's possible, it's not true for every A that's orthogonally diagonalizable. So it would be false there on A. That's not true. So how about B? So let's do this again, do a poll. So does A transpose equal A? So go ahead and do yes or no. Okay, we've got about 10 people responding. So, okay, almost everyone says it's true. So that is correct, because A transpose equals A is the definition of being symmetric matrix. And the spectral theorem says that if A is symmetric, it's orthogonally diagonalizable. And if A is orthogonally diagonalizable, then A is symmetric, as long as it's a real matrix, which we've only been working with real matrices in this class. So B would be true. How about C? There's an orthonormal basis of Rn consisting of eigenvectors of A. Is that true or is it not true? So go ahead and do yes or no again. Okay, we have lots of yeses. And the answer is actually, oops, it's not that one. Yep, it is true. So, oops, where are we at? There we go. Yeah, so there is an orthonormal basis of Rn, and because Q is it's the normal basis of Rn, Q is an invertible matrix, so the columns or rows will span Rn. So that is true. So because of the properties of Q in the orthogonal diagonalization, then that is true. And because we build Q from the eigenvectors of A.
Question on that.
Yeah.
Does that, I mean, so it says it consists of eigenvectors of A, but like if we just went in and solved to find the eigenvectors of A, they wouldn't automatically necessarily be like these same eigenvectors, right? They could just be like scaled versions of these eigenvectors, right?
That's right. Yeah, they would be most likely scaled versions. And even if you have a multiplicity of 2 or larger than, or 3 of larger, you can have, you can create an eigenvector as a linear combination of other eigenvectors. So, so that's possible too. So it's not even just scaled. You can take 2 and make another one. And that's what we do, because we're not guaranteed, if we have an algebraic multiplicity of 2 or more, we're not guaranteed that those eigenvectors are going to be orthogonal. So we have to do Gram-Schmidt to do that. But you'll still end up with an eigenvector after you do Gram-Schmidt. That new vector will still be an eigenvector.
So in the case of this one, it says that it's true. So if there is an algebraic multiplicity of like 2, is it the guaranteed that you're going to have a geometric multiplicity of 2 as well?
Yes. So for symmetric matrices, yes, you always the algebraic multiplicity always matches the geometric multiplicity.
Okay.
So it's always diagonalizable for symmetric matrices. So you don't have to worry about that issue.
Okay.
So good question. Okay. Other questions? Okay. The nullity of A is the multiplicity of the eigenvalue 0. So nullity is it's the dimension of the null space of A. Go ahead and click true or yes or no on your on your Zoom window. Not getting a lot of participation on this one. And it's a bit mixed. So the answer here is true again. You can check the key. Yep. So yep, that is true. Because if you have an eigenvalue of 0, it means it's not invertible. If it's not invertible, you have a dimension of the null space that's 1 or greater, and every multiplicity of the eigenvalue 0 gets you another dimension of the null space. So since it's symmetric, we know that that'll always happen because the geometric multiplicity always matches the algebraic multiplicity for symmetric matrices. Not for matrices in general, or square matrices in general, but always for symmetric matrices. Okay.
So the matrix, it doesn't have to be invertible for it to be orthogonally diagonalizable?
Yes, so that's great. Yes, good clarification. A doesn't have to be invertible. You can have, on the diagonal of D, you can have zeros. That's just fine. So it's still orthogonally diagonalizable. And that can help you to reason through the next one. How about the rank of A equals N? Is that true or false, or yes or no? You do up or down, or can you guys see what other people put when they click on their yes or no's? Yeah, you can. Okay. So you guys can see a few more reds than greens, and so yeah, so no is correct here, because if the rank of A is n, it means it's orthogonal. It means that it's invertible. That's one of the things that's equivalent. It means that all of the rows or columns are linearly independent. It means that yeah, the rank of the null space is 0. The dimension of the null space is 0. But we just talked about how you don't have, that doesn't have to be the case. You can have the rank, you can have eigenvalues of 0. If you have eigenvalues of 0, then A is not invertible, so it can't be full rank, and that's okay, and it can still be orthogonally diagonalizable. So,
Brother Corey, I think Tiancum had a question in the chat. I'm not sure which problem he was referring to, though.
I had a question on if that works for any square matrices about the multiplicity and the eigenvalue 0.
Oh, no, not necessarily. For lots of them, yes, but if you're not dealing with a square matrix, you're not sure. Sorry, not a square matrix. If you're not dealing with a symmetric matrix, then you can your algebraic multiplicities might not match up your geometric multiplicity. It will if they're always 1, but If you have distinct eigenvalues, then you're good. But once you have algebraic multiplicities of 2 or more, then you can get in trouble. So the algebraic multiplicity does not always match the geometric multiplicity. Or maybe we could say, like, there are a couple situations where we know for sure that it does. One is if it has distinct eigenvalues. Another is if the matrix is symmetric. So okay. What were the other questions down here? Oh, question on Zoom. Looks like they answered that. Great. Okay. A inverse is also orthogonally diagonalizable. This is a little bit tricky because A inverse doesn't have to exist. So you might think, well, okay, if A inverse exists, it's orthogonally diagonalizable. So let's change it to that. If A inverse exists, is it orthogonally diagonalizable? Yes or no? Okay, see, I'm seeing lots of yeses come up. So, okay, that is right. And we should be able to prove that pretty easily. If I share my other screen. So if I have A inverse times A equals the identity matrix, then, and I know A is orthogonally diagonalizable, then I can replace A with Q D Q transpose, where Q is an orthogonal Q is Q is an orthogonal matrix. And so what I want to be able to do is say, okay, A inverse equals some P D P inverse, where these are orthogonal. It might not be the same Q, and D might not be the same D. So I'll put D2 there, D1. So here, I'll change that. So I might be getting myself in trouble here. I haven't thought through this a lot. Q 2 2 2 there. So if we call those 1 1 1, then can we algebraically manipulate this here? Well, we could start multiplying on the right by Q. So we could get A inverse Q1D. I times Q will just be Q, because Q transpose equals Q inverse, right? Because it's orthogonal. And then if I multiply by D inverse, so, or 1 over D, we'll just do D inverse on this side. And we can take care of that. And then if I multiply by Q1 transpose, then I just end up with A inverse equals Q D inverse Q transpose. But D inverse is a diagonal matrix with eigenvalues along the diagonal. To get D inverse, I just have to invert every one of those diagonal entries. And so, so that's where my D2 would come in. So, yeah, so it all works out. Yep, and Q transpose end up being the same matrices that we need. So that's how the proof would go. Okay. How about, oh no, what happened? There we go. Eigenvectors from distinct eigenspaces of A are orthogonal. That would be true. So this is always true for symmetric matrices. So it's one of the theorems. Like that's the kind of the crux of the spectral theorem, is that since it's A is orthogonally diagonalizable, well, Q is made by the eigenvectors of A, and Q is or an orthogonal matrix. So so they are orthogonal. At least that for the distinct ones, we know that they are for sure. If they're not distinct, then you're not guaranteed that. So, okay, any questions on this?
So to sum up for F, is it basically like if a matrix is orthogonally diagonalizable, it doesn't necessarily have to be invertible, but if it is invertible, then it is always also orthogonally diagonalizable. Is that true?
That is true.
Okay.
Yep, that's fantastic. Yeah, because we know A inverse, the eigenvalues are 1 over the eigenvalues of A, and the eigenvectors are the same. And so, yeah, once you get Q for A, you actually use the same Q for A inverse. And the diagonal matrix you get by taking 1 over the diagonal entries of D to get your diagonal entries for the orthogonal diagonalization of A inverse. So, yep. Nice. Okay, other questions or comments about this?
What I was kind of confused in the book, whenever there's more than one eigenvector for the same eigenvalues, like if there's multiplicity there, they're not necessarily orthogonal. So if we do the Gram-Schmidt process on it and get it more orthogonal, are they still like, do they still match the eigenvalues that they originally started with?
They
do
do. Yes, they do.
They
so
do?
Yeah.
So there's still eigenvectors of the original matrix. Just
Yeah. Yeah. So if I have V1 and V2 and they're both they both come from lambda equals 2, okay, then any combination, so CV1 plus C1 plus C2 V2, if I multiply that by A, then that's going to end up being the same as just multiplying 2 times C1 V1 plus C2 V2. So any linear combination of eigenvectors with the same eigenvalue, then that's also an eigenvector. Because if you distribute out the A, you get A C1 V1 plus A C2 V2. And then since C1 and C2 are constants, you can pull them out. C1 AV1 plus C2 AV2. And then here, since V1 and V2 are eigenvalues where with lambda equals 2, then AV is this AV1 and AV2 is the same as 2V1 plus and 2V2. And then you can pull out that 2. And so if I pull out that 2, then I get C1 V1 plus C2 V2. So then you're good. But if they didn't have the same eigenvalue, if one of them was 2 and one of them was 3, or one of them was 2 and one of them was 5, then you'd have like a 2 and a 5, and you can't do that pulling out here. So you can't. So then it's not the same. But as long as as long as these vectors come from have the same eigenvalue, then any combination of those, they also give you another eigenvalue that has the same another eigenvector that has the same eigenvalue. And so if these weren't orthogonal to each other, then you can take one, do Gram-Schmidt to get the other one, but Gram-Schmidt is really just taking some combination of V1 and V2 And so so it'll also end up being an eigenvector. Does that help?
Yeah, that makes sense. Thanks.
Great question. Okay, other questions? Okay, do you want to work through, I'm happy to work through another example where we orthogonalize a 3x3 matrix, or I can pull up more final test questions that are related to this. What would you guys like?
Can you do another example?
Yeah.
Sure. Okay. So 2, 3, 0, 3, 2, 4, 0, 4, 2. If we had more time, I'd let you guys work through this, but we don't have time. We don't have time for me to walk through the whole thing, but I've already walked through it, so we can skip some venial steps. So here's A. It's symmetric, so I know it's orthogonally diagonalizable. What's my first step in trying to find the orthogonal diagonalization?
I'm gonna find the eigenvectors, right?
Yeah, find the eigenvectors, which means I have to find the eigenvalues. So the first thing is really finding the eigenvalues. So I'm going to subtract lambda off. So 2 minus lambda, 3, 0, 3, 2 minus lambda, 4, 0, 4, 2 minus lambda. Take the determinant and factor down, and I end up getting 2 minus lambda, a minus 7 plus lambda, and 3 plus lambda. Okay, now I didn't do that in my head. I already worked through this. That was a bit of some figuring out the determinant, factoring things down. So I now know that the lambdas are 2, 7, and a negative 3. Okay, so that's the first thing. So now I have to figure out the eigenvectors for each of those. So let's do 7. So 2 minus 7 is going to be a minus 5. So minus 5, 3, 0, 3, a minus 5, 4, 0, 4, and a minus 5. Augment it with 0, and I'm trying to figure out, the null space of that matrix. That's why I augment it with 0. And so start doing the row reduction. Divide by the first row by a negative 5. So we get 1, a negative 3/5, 0. I can multiply this row by a negative 3 and then add to the second row. So I can get 0. A negative 3 times 3/5 is going to be a positive 9/5. And so positive 9/5 minus 5/5. Minus 5/5 is a negative 25/5. So negative 25/5 plus 9/5, that gives me a negative 16/5. And that stays at 4. Okay, and then if I multiply this row by a negative 5/16 to make that that central value 1, then I get 0, 1. Here I'm going to end up with a minus 5/4, 0, 4, and a minus 5. And now I can get rid of that bottom row. If I multiply the second row by a negative 4 and add, then those will all add to 0. So this will be 0, this will be 0. Take care of that easily. Okay, now I need one last step. I need to use this 1 here and to get rid of this negative 3/5. So I'm going to multiply this row by 3/5 and then add to that one. So I'm going to have 1, 0. And 3/5 here is going to be a negative. Well, my 5 in the numerator will divide out with my 5 in the denominator. So I just end up with a negative 3/4. 0, 1, a minus 5/4, and 0, 0, 0. Okay, so could have been worse. Got some fractions, we're okay. And so now I can think about this as a system. So I end up with x1 minus 3/4 x3 equals 0. X2 minus 5/4 x3 equals 0. And this is a free variable here, this x3. So x3 equals whatever x3 equals. So when I pull everything, all of my x3s over to the other side, I get x1 equals 3/4 x3, x2 equals a minus 5/4 x3, and x3 equals x3. So that means a basis, an eigenvector is 3/4. The basis for the eigenspace is a minus 3/4, a minus 5/4, and 1. Okay, so that's for lambda equals 7. So we don't have time to do the other ones, but for lambda equals 2, I got a minus 4/5, 0, 3/5. And for lambda equals a negative 3, I got 3/4, a negative 5/4, and 1. So now I have my 3 eigenvectors, one for each of my eigenvalues. Well, I can write down my diagonal matrix because it's 7 to a negative 3. Does not matter what order I put those in. Okay, what about my Q over here? Well, I can't just write down these. I just can't put down those eigenvectors because I need Q to be an orthogonal matrix, which means I need the columns to be orthonormal. So I need them to have a length 1. These are already orthogonal. I don't even have to check that because we've got the theorem says that if you're dealing with a symmetric matrix, then eigenvectors of distinct eigenvalues are orthogonal. But they're not of length 1 necessarily. So I could divide. I have to square each of those values, add them up, take the square root, and divide. That looks kind of crazy. There's a little bit easier way. If I scale this one by 4, I just get 3, a minus 5, and 4. And if I scale this one by 5, I get a minus 4, 0, and 3. And if I scale this one by 4, I get 3, a minus 5, and 4. There. That makes it a little bit easier to find the length, because here I can square, I get 9, 25, 16, add all those together, I get 50. So divide by the square root of 50, but the square root of 50 is 5 times the square root of 2. So I can divide by 5 times the square root of 2. It's the same thing over here. I still have 3, 5, and 4. Oops, I missed a negative sign somewhere. Oh, no, this one. I made a mistake. That's a positive right there in x2, so that should be positive. That's not. Otherwise, the one I had for 7 was exactly the same I had for 3, so I knew something was wrong. So here I can divide by 5 times the square root of 2, 5 times the square root of 2, 5 times the square root of 2. In this case, if I square 4 and square 3, I get 16 and 9, add them together, I get 25, square root 5, so that's nice. So now I have, this is my orthogonal matrix, or my, yeah, these are now an orthonormal basis for my eigenspace, and I just have to put those in the right order over here for Q. So 3 over 5 times the square root of 2. So this is 7 here, so I have to take this one and put it here because it corresponds to 7, the eigenvalue of 7. So 5 divided by 5 times the square root of 2 is just 1 over the square root of 2. And then 4 over 5 times the square root of 2. And then a negative. The next one is 2. So my down the diagonal of D, my next eigenvalue is 2. So I go to my second one, the orthonormal eigenvector that corresponds to the eigenvalue of 2. So put that in. And then my last one, which corresponds to an eigenvalue of a negative 3. 3 over 5 times the square root of 2. This one, my 5's cancel out. So I get square root of 2. And then 4, 5 times the square root of 2. Okay, so there you go. And then I can easily put Q transpose over there. So, okay, what questions do you guys have?
Brother Corey Haley has a question in the chat.
Okay, let me find it.
I can just say it. So
Sure.
of A equals, Q dQ, which of those are orthonormal and which of those are like symmetrical and which are triangular? I'm trying to keep track of their properties.
Okay, so Q dQ transpose. This is, yeah, good question. So PDP inverse. So if A is symmetric, so here maybe I should do it this way. So A transpose equals A. So this is symmetric now. So if A is a symmetric matrix, then Q here is an orthogonal matrix. Both of these are orthogonal matrices. And the orthogonal matrix means, it's a little bit tricky because of the name, it means that the columns are orthonormal vectors. They're a set of orthonormal vectors. So they have length 1 and they're all orthogonal to each other. It also means the rows are that. The rows and the columns, they all have the length 1 and they're orthogonal to each other. So, and D here is a diagonal matrix with the lambdas down the diagonal. But so this is only if A is symmetric. If A is square, so if it's symmetric, then it's automatically square. If A is square, then maybe we might be able to diagonalize it if all of the geometric multiplicities match the algebraic multiplicities.
What does it mean for it to be square?
It has the same number of rows as it does columns. So like this is a square matrix, it's 3 by 3. This is a square matrix, it's 3 by 3. 2 by 2, 3 by 3, 4 by 4, 5 by 5. Square matrices are the only ones that can have inverses. Square matrices are the only ones that have eigenvalues. So we deal with square matrices a lot. So if it's square, then we might be able to diagonalize it. The D's would be the same, where it would have that. But if the algebraic multiplicities don't all match up with the geometric multiplicity for all eigenvalues, for all lambdas, then it's not diagonalizable. That's shortcut for diagonalizable. But, and in this case, P and P inverse, they're invertible matrices. The columns are still, if we can diagonalize it, the columns are still like the columns of P are eigenvectors of A, but they're not necessarily orthogonal to each other, and chances are they won't be. So if they are, then A is symmetric. So does that help?
Yes, thank you.
You're welcome. So there's nothing about triangular here in this particular piece. We just have diagonal matrices and we have orthogonal matrices in this case. Here we just have a diagonal matrix and we have an invertible matrix P, which probably is not, could be symmetric, it could be triangular, but it probably isn't. So, okay. All right. Oh, wow, we're over time. So thanks everyone. Study hard. We will see you on Thursday, 2 days. The videos are already up. At least 2 of the videos are already up for the next section, the singular value decomposition. It's a doozy, but it's pretty awesome, pretty amazing. So we'll see you next time. Thanks.